It is, let's see, probability of compound events.
Okay, I'll give it a shot. This is a pretty difficult subject. Go ahead and give me one of the problems.
All right, let's see. All right, so it says, okay. So the directions are find the indicated probability and state whether A and B are mutually exclusive.
Okay.
So it gives us the probability of A is 0.4.
Okay.
And the probability of B is 0.35.
Okay.
And then the probability of A or B is 0.5.
Do they write it like that, or do they use the word or?
They use or. And then we have to find probability of A and B.
Well, you need the probability of A and B.
Yeah.
All right. I don't have my formulas in front of me, but
I have them here if you need them.
okay, yeah. Give me the main formula. I think it's Bayes' theorem.
Yeah, so it's the probability of A or B equals the probability of A plus the probability of B. And that's one of them. And then the other one is just minus the probability of A and B after that.
I'm confused. So the probability A and B is the next thing?
No, so.
Oh, probability of A or B is, now I got you. Probability of A plus probability of B minus the probability of A and B, right?
Yeah.
And this one only applies if there is some overlap. In other words, if there's no overlap, then it's simple.
Right.
It's just probability of A plus probability of B. But if there is some dependency between A and B, which there is, in other words, if there's no dependency, that'll be 0.
Right.
If there's a dependency, that'll be some number. So what we want to do is we want to solve for the probability of A and B. I'm going to move that the other side of the equation, so I have the probability of A plus the probability of B divided by the probability of A or B. And we have numbers for everything on the right side of the equation. Right?
Yes.
Probability of A is 0.4. Probability of B is 0.35. Probability of A or B is 0.5. So we have 0.75 divided by 0.5. What is that? 1.5?
I'm going to do that real quick.
Yeah, it is.
Yeah, 1.5.
Something about that bothers me. First of all, we have a probability greater than 1.
Mm-hmm.
That doesn't seem right.
Would we
Sure, we got let's see, when I did the algebra on this, I added the probability A plus B. I gotta subtract that, not divide by it. Here's an excellent example of ballpark check. In other words, the probability came out to be greater than 1. That can't be. See this equation on the lower right?
Yep.
Well, if I add probability A plus B, that puts it on the left. But then I have to subtract. So I got the probability of A plus the probability of B minus the probability of A or B. And now we got 0.75 minus 0.5, so this is equal to 0.25, which is at least less than 1.
Yes.
So it's a possible answer. Just always know that is if you make a mistake and you get probabilities greater than 1, that tells you you've made a mistake.
Right.
Okay. What else?
So I just have a quick question.
Uh-huh.
So if we use the equation probability of A or B equals probability of A plus B,
Uh-huh.
that equation works. Does that mean they're mutual?
Mutually exclusive, yes.
Okay.
Well, actually, you know what? The first equation should never be used.
Okay.
This is the equation that should always be used because if they are mutually exclusive, then the probability of A plus and B is always 0.
Okay.
So this equation here works for all situations. This equation only works if probability of A and B is 0. In other words, if they are mutually exclusive.
Okay.
So let's see. So that's the main formula. The probability of A or B equals probability of A plus probability of B minus the probability of their connectedness, which the overlap. And that makes a lot of sense. Okay. What else you got?
So there are a few probabilities
Okay.
of complements, it says.
Of what?
Of complements.
Okay. Which merely means one minus the probability of the event. In other words, if I said to you the probability that it's going to rain today is 1/3, then what's the probability that it's not going to rain?
2/3.
Yeah, it's 1 minus the probability that it's going to rain. And that's what they're talking about when they're talking about complements. And a lot of times you have to work with the complements. For example, if I said the probability of rain today is 0.3, and the probability of rain tomorrow independently is 0.2, what is the probability that it won't rain? In other words, what is the probability of no rain either day? This is a problem where you have to work with the complements. In other words, what's the probability that no rain today?
0.7.
Okay. What is the probability of no rain tomorrow?
0.8.
So what's the probability of no rain on both days?
Is it the average of those two?
No, you multiply. In other words, if two events both have to occur, then you multiply. Are you familiar with the deck of cards?
Yes.
If I want to know the probability of getting 2 aces, well, there's 4 aces out of 52. So the first card I got to get is an ace. But then the second card, there's only 3 aces left out of 51. So for me to get 2 aces, I have to multiply. Both of them have to succeed.
Okay.
So when it's an and situation, you're multiplying these two numbers. So the probability of no rain is 0.56. But notice that I couldn't do it based on those numbers. I had to work with the complements.
Right.
Because no rain on either day means no rain tomorrow and no rain today and no rain tomorrow. So both of these have to occur. All right, go ahead and give me your problems.
Okay, so it says the probability of A is 0, and we're supposed to find A prime.
Okay. A prime being the probability of no A. That's the it's got to be 1.
Oh, because it
I
has to add.
believe A prime means the probability of not A, correct?
Yeah.
Okay. Well, all probabilities have to add to 1. So if there's only 2 possibilities, an A or a no A, then the probability of no A has to be 1.
Right. Okay.
If there's some other possibilities, like there could be a B, well, then that changes things. But sounds like from the way you read this that there was only 2 possibilities, A or no A. A or A prime.
Okay. That makes sense.
It's kind of like rain and no rain. It's got to do one or the other. So
Right.
you have to add to 1. Well, some of these aren't too tough. Probability problems can get really, really tough. Probably they don't get that tough until you get to pre-calc. And then you can get some probability problems that are really tough. Especially, combinations and permutations and those kind of problems.
Okay, yeah.
Have you had that? Have you dealt with NCR and NPR?
Yeah, we've done that a little bit.
Okay. So far, we haven't needed that in any of your probability problems.
Yeah.
However, let me give you an example.
Okay.
How many different 5-card hands can be dealt from a 52-card deck?
Would we do 5 over 52 and then 4 over 51?
Well, first of all, let's set it up like this. We've got 52 cards, and I want to arrange them. How many ways can I arrange those 52 cards 5 at a time? And the difference between combinatorics or combination and permutation, combination does not care what order they come in. Permutations do.
Right.
Well, with a deck of cards, when you get that 5-card hand, you don't care which order it's in. If it's a royal flush, it doesn't matter whether it came ace, king, queen, jack, 10, or whether it came ace, jack, queen, 10, king. It's the same 5-card hand. Okay? So this is the way you do it. Now, typically, you're going to do this in a calculator, but it's nice to know what it means. And what it means is 52 factorial divided by 47 factorial, the difference, times 5 factorial. And we can actually almost do that without a calculator. Turns out to be a pretty enormous number even still. But you would expect that. How many 5-card hands can you deal from a 52-card deck? It better be in the millions.
Yeah.
Incidentally, I always like to point this out to a student. You know what that means, right? 50 factorial?
Yes.
What kind of number do you think that is? Take a
Uh,
wild guess. Is it a
uh,
million? Is it a 10,000? What is it?
I would guess trillions.
Trillions. A trillion is 10 to the ninth is 1 trillion. No,
Because that's 50 times 49 times 4.
It's 3 times 10 to the 64th power.
Oh, dang.
That is more molecules than exist in the entire universe. 3 times 10 to the 64th power. There's only like 10 to the 50th molecules in the observable universe.
Wow.
And yet, 50 factorial. That always shocks me and anybody that I point it out to. Because you wouldn't think that 50 times 49 times 48 all the way down would be such a humongous number. But it is. If you put that into your calculator, some calculators, that'll make it cough. You know, it'll say line error. But if you use a new enough calculator, it'll give you the answer for 50 factorial.
Yeah, it's huge.
So this number up here, even though it's only going to be 52 times 51 times 50 times 49 times 48, notice the 47 factorial takes care of everything else. That's the way you do those problems. And I still got the 5 factorial, which is 5 times 4 times 3 times 2. So that number still is going to be in the millions. All right. What other problems do you have?
Okay. The next one's a word problem.
Okay.
It says an employee of a large national company is promoted to management and will be moved within 6 months.
Okay.
The employee is told there is a 33% probability of being moved to Denver, Colorado, and a 50% probability of being moved to Dallas, Texas. And then it says, what is the probability that the employee will be moved to Dallas or Denver?
Well, what do you do with ors? This is similar to the rain problem.
Do you add them together?
Well, let me think for a second. I think you do. Problem is, do you ever get over 1 when you do that? No, there's no overlap here. So you could actually look at this 2 different ways. Yeah, I'm 90% sure you add them together. But let's talk about how we can prove it. Okay? So if there are only 2 possibilities, then the probability of what? Not being transferred?
It asks for what's the probability that the employee will be moved to Dallas or Denver.
Okay, so since that only adds to 0.83%, there must be another possibility.
Right.
Which is either not transferred at all or transferred somewhere else. And we know that has to be 17%. If there's only 3 possibilities.
Right.
Okay. Well, not transferred, the complement of that is 83%, and that's what it would have to be. In other words, he's either going to not be transferred or he's going to be transferred to Dallas or Denver. One of those 2 possibilities.
Right.
So you do add them when it's an or. Let's go back to the rain. Probability of rain today is 0.3. Probability of rain tomorrow is 0.2. This probability of rain either day.
Is it 0.5?
Well, I think it is.
Wait.
There's a problem with this logic, though.
Yeah.
What if I had 6 days in a row? And the probability of rain on each day was in these neighborhoods. And I said, what's the probability that it will rain either of the 6 days? Can't just add them together. You'll get a probability greater than 1.
Right.
So that's why you have to work with the complements.
Oh, do you multiply?
No, you don't multiply either. I don't know. I'm going to have to... well, let's deal with your problems instead of me making some up, because we may be able to figure out all your problems. Almost. Do you have answers on these by chance?
Yes.
Check that last one. Is it 83%?
Let me see. I don't know if they have it for this one, because
Or Denver?
this was an even numbered problem.
Okay.
But they have answers for
Have the
all.
odds.
Yeah, so we
Odd
could
one
do.
similar?
Yeah.
Okay, let's look at that one.
All right. So it says, you and your best friend are among several candidates running for class president. You estimate that there is a 40% chance you will win the election and a 35% chance your best friend will win.
Like that?
Yeah.
Okay.
And then it says, what is the probability that either you or your best friend will win the election?
Okay, let me think about this for just a second. If we add them, it's 0.75.
Yeah.
I think that's the answer. Can you check real quick? If that's the answer, we can go on.
Because that makes sense to me.
Me too. And I think that is the answer, because if there were 4 other candidates, then all the probabilities would have to add up to 1. So
Yeah.
there's no way we're adding up probabilities and getting more than 1 here.
Yeah, it's 75%.
Yeah, it's pretty straightforward. Really, the thing is, when you do or, you add. When you do and, you multiply.
Right.
Okay?
All right. I have a few of these card problems.
Okay.
These are a little confusing.
Okay.
I get pretty much everything else, though.
They're fairly straightforward, I think. Go ahead.
Okay, so these are just saying a card is randomly drawn from a 52 card deck. Find the probability of the given event.
Okay. What's the first given event?
It says a heart or a diamond.
Okay. So, what's the probability of a heart?
13 out of 52.
1/4. Okay. What's the probability of a diamond?
1/4 as well.
Okay.
Wait.
What's the probability of one or the other?
50%.
Yeah, and that really makes sense because half the deck is red and half the deck is black, and this is the red cards.
Oh yeah, that is really easy.
Mm-hmm.
Okay.
What else?
Let's see.
There can be some problems with replacement or without replacement. Have you had any of those?
No, we haven't had those yet.
Okay. When I was doing the probability of getting 2 aces, that was without replacement. In other words, the first ace is that probability. But once you have that ace in your hand, it's no longer in the deck, so there's only 3 aces left, and there's only 51 cards. So this is without replacement.
Oh, okay. And replacement would be putting it right back.
Exactly. If it was with replacement, then the odds of getting the first ace are that. Put it right back, the odds of getting the next ace are also that. So
Right.
it's different. This one comes out to be 1/13th, and this one comes out to be closer to about 1 in 17, which is the true odds in getting dealt a pair of aces and no limit hold'em.
Okay.
As opposed to 1 in 13, because
Right.
it is it's without replacement. Yes.
All right. There's one that says a 5 and a 6.
On a dice.
For the cards.
Oh,
Like
the probability of getting a 5 and a 6?
Yeah.
With replacement or without replacement?
I'm assuming without.
Okay, yes. Okay, so what's the probability of getting a 5?
4 out of 52.
Okay, 1 out of 13. And what's the probability of getting a 6?
Also 1 out of 13.
Well, that's with replacement.
Oh, yeah.
But if you're going to end up with a 5 and a 6 in your hand, then it's got to be without replacement.
Right, so that's 4 out of...
probability of getting the 6? This is 4 over 52. What's the probability of getting the 6 once you've already gotten the 5?
4 over 51.
Exactly. So what's the probability of getting a 5 and a 6? Multiply or add?
Would you add?
No, you add when it's an or question.
Okay.
Right? Probability going to Dallas or Denver, we added them. But if you have to get a 5 and a 6, then the probability of the first card being a 5 is that. Probability of the second card being a 6 is that. However, that is the probability of getting dealt specifically a 5 or a 6. Excuse me. I'm not quite sure what the question asks, but if it asks, what's the probability ending up with a 5 and a 6 in your hand? Well, there's 2 ways you can get a 5 and a 6 in your hand. You can start out getting the 5 and then getting the 6, which is this. Or you can start out getting the 6 and then have to get the 5, which is that. So it's really 2 times that. Is this an odd one?
Yes.
Okay, so this should be 32 over 52 times 51. Whatever that number is should be the answer. You have a calculator and you can come up with that?
The book says it's 0.
Oh, because you're only getting 1 card. In other words, yeah, we didn't get the premise of the problem.
Oh, it's a trick question.
Yeah, it is. If it's
Okay.
0, yeah. And it's really a trick question because the most popular card game right now, or at least poker game, is No Limit Hold'em, where you get 2 cards.
Right.
So if you wanted the odds of having a 5 and a 6 as your starting 2 cards, it's the way we did it.
Right.
If you want the odds of having a 5 and a 6 with 1 card, clearly you can't have both a 5 and a 6 if you only have 1 card.
Yeah.
And that's why they came up with 0. I just wasn't interpreting it properly.
Yeah.
All right, you got any last ones?
No, that covers everything.
I'll take care of you for tonight.
Yep.
Okie dokes. Jake, I'll talk to you next Monday.
Excuse me.
Yes.
So we haven't gotten any bills on PayPal. I
Okay,
feel
that's because I have been negligent and busy. I will get
oh,
right to it. I will send you an invoice. Um,
okay. I felt bad. I'm like, gosh,
no, you don't
I
need to
know
feel
I
bad.
need to
For
pay.
one thing, it hasn't been that many sessions, so it's not that big a number. I usually try to
Okay,
get invoices out before they hit $100, and I'm sure he's under that. So,
okay.
um,
Yeah, no worries. Whatever your routine is,
yeah,
I
no,
didn't know I
I'll
was
try
supposed
to
to
get
pay
one out in
weekly.
the morning.
Okay,
I
no
usually
worries.
try to
Thank
do it
you.
at least at the end of the month. So,
Okay.
but
Sounds
thank you
good.
for asking. So,
Yep.
okay, Jake, I'll talk to you next week.
All right, thank you.
You're welcome. Bye bye.
Bye.